So what he imagined is that you have spinor halves sitting on each circle, okay? And the neighboring spinor half will form a singlet. You know that singlet is completely rotationally invariant. But this spinor half can form a singlet with that guy, or this spinor half can form a singlet with that guy. So what's the choice? And he envisioned a state that the different pattern of singlet formation actually resonate with each other, very much like what you learned in high school, namely benzene. Benzene, as you know, it has two double bond configurations. But in nature, the true ground state is actually a linear superposition of the two different double bond configurations. So this was called the resonating valence bond by Linus Pauling, who discovered vitamin C also. So he borrowed this name and called this resonating valence bond. Spin liquid. Why is a spin liquid? Because it doesn't form a spin long-range order. In the language of spin liquid, I guess a magnetic ordered antiferromagnetic state should be called a spin crystal. So this is a state which does not break spin rotation symmetry and down to zero temperature. And before this, we didn't know, we didn't suspect such a state exists. And after he proposed it, if I had proposed it, nobody would care. But since he proposed it, so people say, what the heck, let's take a look whether such state really exists or not. And I will tell you what's the outcome. Except here, I want to tell you, there are, by now, theoretically, predicted many other examples of quantum paramagnetism. Some of them are actually experimentally observed. And one example is the chiral spin liquid. I won't go into detail. And the other is very hot nowadays, symmetry protected topological state. And the other is the valence bond crystal state. And here, I want to stress that I only care about spin rotation symmetry breaking. I don't care about the lattice rotation symmetry breaking. And finally, what's most relevant to my talk today is the discovery of a new quantum disordered state called nematic quantum paramagnetic. That's what I want to tell you today. And I want to argue for you that this actually is the ground state of iron selenide. And that's the reason that there is no magnetic order observed down to zero temperature, but it breaks the crystal rotation symmetry. All right? So, as you can imagine, for experimentalists, finding this novel magnetic state in real materials is an important subject of condensed matter physics. I would say it is the important subject in condensed matter physics today. Actually, to find quantum disorder state at zero temperature. All right. So, under what condition, for what materials, those novel states can be realized? For the student present, please do not hesitate to ask me questions if it is not clear to you. So, now I want to tell you something which might not be that familiar to you, and therefore I want to go slowly. So the idea is the following. For most of the magnetic system, when you cool it down to low temperature, it will order. It will become magnetically ordered. For if a system remains unordered magnetically at zero temperature, it means something is happening. Something destroyed the magnetic order. And here, I want to argue for you what we know, at least according to the all the past experience, what's the best way to destroy magnetic order is nuclear topological defect. All right, so let me spend one slide and give you an example of topological defect. For example, suppose you have a one-dimensional superfluid at zero temperature, and you like to destroy the superfluid order. And what happened is that such a superfluid order is destroyed by proliferation. Proliferation in Chinese means 扩散, okay? Proliferation, 扩散. Means through the proliferation of vortices, which is the topological defect of the superfluid order parameter. Let me describe that in a little more detail. By the way, everything I said also applied to a planar magnet, namely a magnet whose magnetic moment can only point in the plane. Okay, so let's talk about the planar magnet. That's easier to envision. For a planar magnet, the magnetic moment or the order parameter point to a different direction on a unit circle, right? So a topological defect of a planar magnet is, because I'm talking about a 1D superfluid at 0 temperature, so this is a space-time picture. So the topological defect of a planar magnet is denoted by this red ball here, and around this red ball, if you draw any closed loop around this red ball, you will find that the magnetic moment you encounter will actually will go around this circle once. All right. So no matter how far, but if you draw a loop which does not enclose this red point, then you watch how does the order parameter change on the loop. It will not enclose the circle once. So this is a topological defect. In the highbrow language, in topology, they say pi1 s1 is equal to z. Okay, so that counts. How many times as you go around the center of the vortex, the order parameter will wrap around the unit circle. It can wrap it by an integer number of times. So
this is a space and time that you go around, the time becomes negative. You have to invert the time.
Yeah. So yeah. So
this is very different from if you just envision from the space.
From the space, right? So, but you should know in quantum statistical mechanics, our time direction is actually cyclic. This is the imaginary time.
Okay. I have a trouble actually.
Yeah.
To envision this in the condensed matter.
Yeah.
Because the time error usually is fixed in condensed matter and never flip.
Well, due to the due to the density of state, reasoning that the time seems to flow always forward. Although all the microscopic interaction are time reversal invariant.
Microscopic, yes.
Yeah, yeah. So here, for condensed matter physicists, when we talk about such a phenomenon, time is just a parameter, just like space.
Okay, that's how you treat it.
Yeah, just like space. It's just a parameter.
But is there any meaning afterwards?
Yeah.
This time?
Yeah.
Is it evolution?
Yeah. So here it really means the quantum statistical mechanics is talking about the evolution of the partition function, right? So it's e to the minus beta h. So in real Minkowski time quantum mechanics, the time evolution operator is e to the it times h. So this is like changing time to imaginary. Then you get to quantum statistical mechanics. So in this case, when we talk about quantum statistical mechanics, this imaginary time is even cyclic because in computing the partition function, you take a trace. That means the initial and the final state are equivalent to each other. So in the time direction, it's really cyclic. So at this moment, please just take my words. Regard time as a parameter, and without worrying too much about what does reversal of time mean. All right. So, but you can easily imagine that if I pop out those vortices here and there, then by the way, in this picture, a completely superfluid order state should be drawn as a picture that the arrow will be completely aligned across the space and for every time slice. Okay. So that's a completely ordered superfluid state. You can clearly see if I nucleate those topological defects, I would destroy the superfluid state. So now I want to talk about an analogous topological defect for a magnetic order state. unlike, oops, this is very bad. Somehow I didn't draw. Okay, here, let me draw it here. So the magnet, so unlike the superfluid state or the planar magnet, the order parameter of an isotropic magnet live on the unit sphere rather than the unit circle, S2. Okay. So this is the, this is the magnetic order parameter, and somehow this topological defect in the magnetic order, I will show you very soon, will involve some very fancy structure in this type of magnetic order parameter. But before I do so, I want to tell you something. I told you before that Phil Anderson proposed this fascinating resonating valence bond state, and since his track record is so good, so after the 1987 proposal, condensed matter theorists were crazy looking for such a resonating valence bond state, but we never find it. There are so-called circumstantial evidence in here and there that we find it, but there's no hard evidence for it. So what happened is that what is the strategy that condensed matter theorists use to find such a state? So so condensed matter theorists, like anybody else, they start with a Hamiltonian, a quantum Hamiltonian, quantum many-body Hamiltonian, and ask what's the ground state of such a quantum many-body Hamiltonian. And like it or not, for 99.9999% of the Hamiltonian you write down at 0K, it is magnetically ordered. So then what condensed matter physicists decide to do is they will introduce interaction with conflicting, conflicting desire. So let me give you an example. So suppose I take a square lattice and I turn on a nearest neighbor interaction which favor the magnetic moment to anti-align. Okay? So such a interaction can be easily satisfied by such a magnetic order state. That's called a null state. Now, what condensed matter physicists do is then they turn on a second neighbor interaction, which also prefer this two magnetic moment to anti-align. As you can see, then the desire of these two type of interaction conflict each other, and they are hoping that when I introduce sufficiently strong second neighbor interaction, I will destroy this magnetic state. That, in condensed matter physics, such a phenomenon, namely you have a conflicting interaction, is called frustration. So this reflects a frustration of the system to decide what pattern to order. Okay, so it's a frustration. So condensed matter physicists for the past almost 30 years has been introducing frustration of this type, of that type, any type we can consider, and in hoping we'll find this very novel resonating valence bond state. But we don't find it. Instead, we find this valence bond crystal state. So what does this picture mean? This picture means that the spin-a-half, for spin-a-half system. Why for spin-a-half system? Because the copper oxide superconductors, before you inject any carrier to it, each copper carry a spin-a-half. So this picture means that the two spin-a-halves living on these two black dots, they form a singlet. And the singlet is denoted by this blue segment. Okay? So, but however, different from what Anderson proposed, those are pattern of pairing, the singlet pattern do not resonate. They actually remain static in a regular pattern. They form a so-called valence bond crystal. Each of this pair is called a valence bond, and they form a crystal pattern. So in this case, you have this pattern, and that pattern can be obtained from this pattern by just shift the pattern on the left by one lattice constant. You will get from here to there. And here, this pattern is obtained from that pattern. sorry, this pattern is obtained from that pattern by a rotation of 90 degrees, and this pattern is obtained from that pattern by rotation of 90 degrees. So if you have a square lattice system and you introduce whatever frustration you like, you find that instead of finding this resonating valence bond state, this is the state you find. The system forms a valence bond crystal. And this, you know, in fact, this type of valence bond crystal has been found in real materials. But here, then there's a very curious fact. You see, we start with the Néel ordered state, and we introduce what I call frustration to destabilize the magnetic ordered state. Instead, once we restore the spin rotation symmetry, because although they are, you know, those valence bond crystal patterns, they break translation symmetry, they also break rotation symmetry of the crystal, but they don't break the spin rotating symmetry because each one of them is a singlet. So it's a very curious fact that upon restoring the spin rotation symmetry, the breaking of the spatial translation and spatial rotation symmetry will immediately follow. This is very, very strange. Why, after restoring the spin rotation symmetry, it necessitates the breaking of spatial translation and spatial rotation symmetry? This has been bothering us for years. And it turns out that this fact has a topological origin. And that's due to a phase, what we call the Berry phase. And that's what I will explain to you right now. Are there any questions about the fact? Yeah.
Are they degenerate?
Yeah, they are degenerate.
So they have
This valence bond crystal state, they are the zero temperature state, and this four pattern has the same energy. Except if you have a boundary, which is, if this is a finite system, then it might choose this and that rather than this and that.
So if they are degenerate, why the linear combination of this cannot be a ground state?
Yeah, okay, that's a good question. Because if I want to make a linear combination of this and that involves what we call macroscopic quantum tunneling. Because that means if you go from this state to that state, that involves the change of a macroscopic number of degree of freedom. And macroscopic quantum tunneling is the quantum tunneling amplitude is done exponentially small if the system is exponentially big. But you are right. Those four patterns are exactly degenerate with each other. So if a real system realizes one of the patterns, it means it also spontaneously breaks symmetry.
The quantum number for spin can affect the behavior here. You are talking about
Spin a half, exactly.
So it will change. So this is the key.
Yeah. This is the key. Yeah, you got it. Yeah. So now, let me tell you how are those valence bond crystal states are produced. And when we introduce what I call frustration, what happens? And this will take me back to talk about the topological defect of the Néel order parameter. Unlike a planar magnet, in an isotropic magnet, the magnetic moment can point anywhere on the unit sphere. So this guy lives on the unit sphere, and so therefore the topological defect I'm talking about will be some singularity in space and time, because all the high temperature superconductors under consideration, such as carbon oxide and iron-based superconductor, they are quasi two-dimensional. You can view them as layers, and you can just take a single layer and consider them. They are quasi two-dimensional, so it must be there must be a topological defect in two-dimensional space plus one-dimensional time. In 2 plus 1 dimension, there must be a topological defect whose proliferation is responsible for destroying the magnetic state. And what are those? So let's not look at this at the moment. Okay, let me show you a single pattern. In this pattern, I'm showing you the Néel order parameter. What I ask you to imagine is you have a square lattice, and the system becomes Néel order. So, but what I ask you to do is don't look at every lattice site, look at every other lattice site. And that is the order parameter of the Néel order. So in the Néel ordered state, such an order parameter is completely aligned. So now, this is a spatial pattern of the Néel order parameter, but we know the Néel order parameter actually live on the unit sphere. So you can ask yourself, if I transplant all those arrows onto the order parameter space, where does it go? It just goes to one point. Okay? So this mathematician called a mapping from the physical space to the order parameter space. The physical space here is two-dimensional, x and y direction. A particular pattern of the order parameter is a mapping between the physical space and the order parameter space, namely the unit sphere. All right? Okay, is that clear? So this is a trivial mapping. This is a trivial pattern. Here is a less trivial pattern. First of all, not all the arrows are aligned. And actually, the arrows has a very intricate structure. But if you look at the arrow very closely, and again, you transplant each arrow onto the unit sphere. For example, those guys along this column will be mapped onto the North Pole, and so does all the arrow on the perimeter. But when you come to the middle, you begin to map to some other point. So if you actually look at this pattern and do this mapping, you will find that very amazingly, this pattern actually, when all the arrows are transplanted onto the unit sphere, it covers the unit sphere exactly once. Okay, just like in the previous case, when I draw a circle enclose the red dot, it actually map onto the unit sphere, unit circle once. So here it map onto the unit sphere once. And in two space dimension, in mathematics, we know there's a mapping. If you have a unit vector field defined as a function of x and y, there's actually a topological invariant which tell you the pattern of this order parameter wrap the unit sphere how many times. That's called the skirmion number. Okay, so that's not a big deal. It's just a jargon. So the bottom line is that if the spatial dimension is 2, then any patterns must cover this unit sphere integer number of times. So what is the topological defect? Well, the topological defect is again a singular event in space and time. The space is x and y direction, and this is the time direction. At some point, okay, you find that this covering number can jump. Okay, it actually in this particular case it jumped by 1 because it changed from 0 to 1. And such a pattern has been called the Néel monopole. Well, it has a very bad name. It's called the Néel monopole. Well, one thing you can understand why is it called a monopole, because this wrapping number is all of a sudden not conserved at this point. Just like the magnetic charge not conserved at a magnetic monopole. So this is called the Néel monopole. One thing you can appreciate is that if such a Néel monopole proliferates, namely monopole can pop in and pop out all over the place, of course this regular Néel pattern will be destroyed. Okay, but after the Néel pattern is destroyed, what happened? It turns out that this is really a great work, a seminal work done by Duncan Holden, who's a professor at Princeton, and he is very original, and he has come up with so many novel condensed matter ideas, and actually his idea, he wasn't trying to describe what I'm telling you, but he find that this topological defect here actually carry with it a phase factor when you talk about the Feynman path integral. So look, I don't want to go into detail, but if you ask a condensed matter theorist how to describe a quantum magnet, what they will do is that they will consider space and time. over space, you will have different magnetic moment configuration. Those configuration can change. So you integrate over those configuration and integrate over the space-time of such configurations. And those configuration in particle physics is in a continuum that's called field. So here, in their language, it's a vector field. Okay, so you just do the Feynman path integral over the vector field. But unlike usual Feynman path integral, once you have a actually topological defect in the Feynman path integral, you find that actually this topological defect carry with it actually a phase factor, and that phase factor depends on I said that topological topological defect is a defect in which that covering number can change by integer. So it depends on how much that integer change. Namely, is delta QS equal to 1, just as I show you, or delta QS is equal to 17, or delta QS is equal to 100. So it depends on how much it jumps. And moreover, it also depends on the exact location of this magnetic monopole when projected into the space slice. Okay, so this is time. Space is a square lattice. So he has shown that this so-called Berry space has such a 4 sublattice structure. Is I. I is the square root of -1, right? So I raised to delta QS. So if you sit in the even plaquette, is this number. If you sit in the even odd plaquette, is this number. If it is odd even, it is this. And if it is odd odd, it is this. So you have a 4 sublattice structure. So now we can simply plug in numbers. If delta Q is equal to 1, namely if the defect is like what I show you, the Berry space will be amounts to I minus I and 1 minus 1. Guys, if this is what's happening, then this topological defect cannot proliferate. The reason is that if the topological defect proliferates above this plaquette versus above that plaquette versus above that and versus above that, their phase destructively interfere because it adds to 0. So they cannot happen. So this topological defect will never, proliferate. You do the same arithmetics, and it happened that for delta Q equal to 2, the same thing is true. Although the phase is different now, but again, if you add the phases, they add to 0. Delta Q equal to 3 is the same, and you add to 0. Now, once you hit delta Q equal to 4, all the phases, I to the 4th power will raise to 1, and all the phases become the same. So this immediately tells you that this Néel monopole cannot proliferate. This type of Néel monopole cannot proliferate. This cannot proliferate. This can. It can proliferate, and in fact, they constructively interfere. They can proliferate. So what does that mean? That means the following. Here, I'm drawing you, here, each of the little square is a space slice. So each space slice, as I tell you, this all the parameter pattern associated with it, you can compute a wrapping number. So in this particular time sequence, the wrapping number always change by multiple of 4. So this can happen because the magnetic monopole associated with delta Q equal to 4 can proliferate. And here is another time sequence where again the different time slice, the wrapping number change by multiple of 4, and it can happen. And so is here, and so is here. So those are all possible time sequence. But there cannot be a time sequence where this wrapping number change from 0 to 1. So in other words, for each time slice, there is actually a conserved quantum number, namely Q, is conserved the mod 4. So if you look at all those slices, Q is equal to 0 mod 4. And for this slice, Q is equal to 1 mod 4. And for this, Q is equal to 2 mod 4. And for this, Q is equal to 3 mod 4. For all those time sequence, they can happen. And when the monopole